It's a real pleasure to host Piero Madau for today's colloquium. Well, it's also embarrassing to give a presentation of Piero's scientific activity that will take a lot of time, but we try to be short. Piero started in Italy in Firenze, where he got the laurea thesis, then he moved to Sissa for the PhD, and then to various places in the United States, Caltech, Space Telescope, and now in Santa Cruz with 1 year in Cambridge. Okay. And well, it's famous for many seminal papers in the field of extragalactic astronomy and cosmology. And today we talk about the dark and light side of galaxy formation. At the end of the talk there will be a light refreshment here, wine and cheese, so please do not disappear. You have the opportunity to make additional questions and to chat a bit with them here.
Thank you very much. It's a real pleasure to be here, to see so many friends and old colleagues. I've not been here, I think, for a while, so I'm enjoying this visit a lot. Today I'm going to tell you a little bit about galaxy formation. It's going to be a generic talk about galaxy formation. I've given more specific talks over the last few years, and as a theorist, they always end up, quibbling with your particular feedback implementation and whether the hydro solver that you're using is trustable, etc., trustworthy, and so I got a little bit fed up of it. So I'm going to step back from the details and just give you a broader overview of where we are, I think, in galaxy formation studies. So let me start by reminding you that galaxy formation, the sort of dot-com of astrophysics, is a field that has seen some fantastic growth over the last 20 years. It's not the only field. Other fields have of course, exploded, like extrasolar planets. But I think it's still fair to say that a lot of people, astronomers, work in galaxy formation. And if you step back a little bit from the details, you realize that galaxy formation is about nothing less than the origin and 14 billion years evolution of the building blocks of our universe as a result of quantum fluctuations. That's the idea. We see those fluctuations half a million years after the Big Bang imprinted in the cosmic microwave background. We think that those are quantum fluctuations amplified perhaps by a phenomenon called inflation in the aftermath of the Big Bang. And so to address galaxy formation properly, you have to follow the dynamics in an expanding universe of the dark component, of the dark matter, as well as of the baryons. And so it's sort of a grandiose enterprise that starts from the very early universe and ends up today. And as such, is not for the faint of heart. Galaxies are molded by highly nonlinear processes that are happening on a variety of scales, from the small scales of star formation and accretion onto massive black holes, which is the regime where ordinary baryonic matter dominates, up to the very large scale of the cosmic web, which is the realm of non-baryonic dark matter. And it is this, highly nonlinearity as well as the dynamic range that makes hard for theorists to address the physics of galaxy formation, in fact, and create, make testable predictions. So let me also start to remind you that we live in a nearly perfect universe. You've seen this plot very many times. This is the angular power spectrum of temperature fluctuations in the cosmic microwave background. If you want, it's the variance of the brightness of the spots in the CMB versus the size of the spot. And, the green light there, the green curve, is the best fit model, which we call lambda CDM. It's a 6-parameter model. And you should look at this again with new eyes and realize that it doesn't happen very often in astrophysics that a model fits the data so well. Okay, I don't know very many examples, perhaps you can correct me. Maybe Sinjad Zaldovich, but not even in that particular case. You get such a good fit to the data. So those 6 parameters, it's a 6-parameter model. I was telling you the 6 parameters are listed here after the latest Planck data release. Is the baryon density here. This is in units of the critical density, so we call it omega. the baryon density, the density of cold dark matter, the position of the first peak of those anisotropies, which is proportional to the horizon scale at recombination, the optical depth to reionization, because the universe gets reionized at late time, and so those photons will scatter CMB as they propagate CMB photons, the electrons will scatter CMB photons as those photons propagate to the Earth, and we can measure that. And then two parameters, the index of the power law primordial power spectrum and the amplitude. Okay, so these 6 parameters are what enters into those fluctuation anisotropy best fit models. And so you just look at the numbers there, you realize that we have today 160 sigma measurement of the cosmic baryon density, 120 sigma detection of non-baryonic dark matter. And so, if you are as old as Ciotti here, who is smiling, and so you remember, cosmology maybe 20 years ago, you realize that 20 years ago we were relying to get the baryon density, we were relying on Big Bang nucleosynthesis, and that data were not particularly good or as good as this. People did not believe it. Otherwise, we would not have spent millions of dollars to look for matches in the halo of the Milky Way. Okay, so the idea here is that perhaps there is some thermal relic, that's the dark matter. In lambda CDN, the C is for a cold. So there is a cold, we don't really know whether it's cold. It's sort of cold, it could be warm, tepid if you want, stable, weakly interacting massive particles which arise from the extensions of the standard model of particle physics, and it is this particle which dictates the formation of cosmic structure, at least on large scale. Okay, and so if you know a little bit of cosmology, you know that you can integrate the Boltzmann equation. N sub x here is the proper density of dark matter particle. You write a Boltzmann equation where the density of your dark matter particle is dropping as as the universe is expanding. There is a term here which is proportional to the self-annihilating cross-section. And so once you solve the Boltzmann equation for a given cross-section, you find, in fact, that at any time the co-moving density of dark matter particle will drop as the universe is cooling down. At equilibrium, that's just a drop to the Boltzmann factor. And at a certain point, the abundance will freeze out. That happens at decoupling because the interaction rate becomes longer compared to the interaction timescale become longer compared to the expansion timescale. And so what you expect from this type of picture is that the higher the cross-section, the longer that particular particle will stay in equilibrium, the smaller is going to be the abundance today. And if you want to explain the dark matter that we see today with some relic particle, a thermal relic of the early universe, you end up with what you call the Wimp miracle. In other words, to get the omega matter that we see today, which is about 0.12 in that units, if you plug in a cross-section, which is typical of weak interaction cross-section, you basically get the right amount of red particle today to explain dark matter, and the thermally average cross-section that you need is about 3 × 10⁻26 centimeter cube per second. So remember this number, because it's going to come out later. So, if this were the physics of the early universe, then we would explain, of course, the dark matter with some particle that exists beyond the standard model of particle physics. Now, of course, we don't know what that particle is, and you might think that dark matter, in fact, is sort of a nuisance. But without dark matter, we have no idea how to make galaxies. This is, again, the same power spectrum. There's plenty of physics in the anisotropy pattern as a function of angular scale. The scales we are interested in today are the small scales, the scales of galaxy formation. And you see the anisotropies are tiny. The universe is very smooth on these scales, at least when it comes to temperature fluctuations and baryon fluctuations. And that's due to silt damping. That's after geosync. who first investigated this type of process. And what happens at recombination is that because of the mean free path of photons is finite, close to the recombination epoch, and so photons can diffuse out of high density region into smaller density region, and in doing so they are going to drag the baryons and wash out fluctuations on the scales of galaxies, on small scales. Okay? So if we were living in a universe that only had baryons, basically from the recombination epoch, which is a ratio of 1000 down to z=0, because the fluctuations are so small, there would not be enough time to create nonlinear structure today, like galaxies, clusters. Okay, there's no self-dumping, of course, for dark matter, so dark matter fluctuations can grow before the epoch of recombinations, and so you get a head start in galaxy formation because of the presence of dark matter. There is no dark matter, we don't know how to make galaxies out of gravitational instability. You have to make up a different type of scenario. So as some of my particle physics colleagues say, dark matter in fact is our friend. So lambda CDM has had great success in explaining the large-scale distribution of mass in the universe. However, the nature of the dark matter particle is best tested on small scales. Small here means subgalactic scales, the scales of dwarf galaxies, the scale of cores at the center of galaxy, because it is on those scales, in fact, that, if you have a warm dark matter instead of a cold dark matter, if you change the mass of your dark matter particle, if you change the interaction properties of that dark matter particle, it is on those scales, in fact, that you can test the nature of the still unknown dark matter. Okay, exactly on those scales, those are of course small scales, they're also the scales where baryons dominate. And it is on those scales that lambda CDM has had a lot of problems, the small scale crisis of lambda CDM. It is on all scales, on those small scales, that there are several discrepancies between the expectations and the observations. So this is the mass variance. It is, you can see it very well, but it is delta m over n as equals 0 as a function of mass scales. And here I have a bunch of probes from large scale, that's the cosmic microwave background, down to the abundance of clusters, lensing the large scale structure as seen in the Sloan Digital Sky Survey, down to the scales of the Lamin alpha forest. And the dashed line is, again, is a cold dark matter scenario. Again, there is perfect agreement from the CMB down to the scales of the Lamin alpha forest with expectations from lambda CDM. On smaller scales, these are the scales, as I was telling you, of galaxy core, dwarf satellites, gravitational maybe lensing. On those scales, then the comparison between the expectation of the theory and the data, it's uncertain, and CDM doesn't seem to be doing that particularly well. And that has given origin to what we call the small scale crisis. And so small scale, the crisis that is in the news extremely often, terminology like the core cusp problem, the missing satellite problem, too big to fail, the angular momentum catastrophe, always come from comparing subgalactic structure to the expectation of cold dark matter and finding, in fact, that you're not doing particularly well. Incidentally, I didn't say that, but please feel free to stop me at any time and ask questions. Okay? We don't need to have all questions at the end. So, those discrepancies, or at the origin of those discrepancies, often there are n-body simulation. So in n-body simulation, you have to follow the nonlinear dynamics of the dark matter. When you do an n-body simulation, basically what you assume is that the entire density parameter is in some cold particle that interacts only gravitationally. There is no other type of interaction. A conditionalized particle which you try to sample with as many particles as you can. And if you want to simulate a galaxy halo, the best type of simulations today, n-body simulation, can push the number of particles to about 1 billion. Okay, that's state of the art. A few billions, maybe. It has been like that for a few years now. Okay, it's very difficult to do. It's impossible to do things that are much more expensive than this, or have many more particles than this. You can do large-scale structure simulation with 10 billion particles. But that's because the dynamical time scale on large scale is much longer, and so you don't need to integrate the same equation on much shorter time scale. If you want to simulate a halo of the Milky Way, a few billion, it's basically state-of-the-art. So you have a simulation of collisionless dark matter particle of a few billion particles. You know that this is a bad approximation in the center of massive galaxy because there are no barriers in this type of simulations. And so you know the gas will have some effect. It's okay in galaxy halos. It's also okay when you're trying to simulate faint dwarfs. Some of the faintest dwarfs that we see in the halo of the Milky Way today have mass to light ratio of 1,000. So for those type of systems, the stars that you see are just test particles moving in the gravitational potential of a dark matter halo, and so an n-body approximation to simulate those systems is perfectly fine. The physics is simple; it's just gravity, and that allows you your supercomputer simulation to scale well with CPU. And that allows also high spatial and temporal resolution because you don't have to integrate the aerodynamic equation, which is expensive. So there are no free parameters. The initial conditions are determined by the cosmic magnitude background fluctuation spectrum. I take that fluctuation spectrum, that amplitude extrapolate on smaller scales, which is exactly what you would expect in cold dark matter. You run a simulation without any free parameter. Okay, don't think there are lots of knobs that are turned. The only free parameters you have is you identify a halo that you think looks like a Milky Way. So the mass of your host halo perhaps is a free parameter, but nothing else is. So there are no free parameters, or almost no free parameters, and you get an accurate solution to the idealized problem because there is no gas, there is no star formation, there is no energy feedback in the interstellar orbit. So an n-body code is, just to give you some feeling of the complication here, the set of equations that you have to integrate is not that large, and they're not particularly complicated, okay? This is just the force equation. You take the force equation and the Poisson equation, and you solve them in an expanding background, okay? Simple physics. The problem is, of course, if you want to simulate the gravitational interaction of billions of particles, then you need some fast way to compute interaction with those particles, because if you do it particle by particle, then the time spent on doing this force calculation will scale as n squared, which is killing. Okay? So the way to do it is you develop a tree code. In fact, you don't even have to develop it. There are 3 codes available on the web. We do a 3 code where you do a partition on the volume. And of course, if that's the particle I want to compute the gravitational force on, then I want to get that force at high precision for nearby particle, but then because gravity becomes weaker as I go further and further away, at large distances, instead of dealing with particle-particle interaction, I can do a cell-particle interaction. Okay, I group all my particles, there is a central mass, there is a total mass, and I compute the gravitational force from that far away cell to here. Okay, and that only scales as n log n, which makes feasible to run simulation in a million particles. Okay, so an n-body code is relatively simple, except for this octree, which is the way you compute, you partition your volume and you compute gravity. The other type of approach you want to use if you want to follow the nonlinear dynamics of the formation of an individual galaxy is the fact that you want to put your supercomputer time where things are happening. And so you do a zoom-in simulation. You have a large box here. In this particular case, this is a 40 megaparsec box. And this is the region which will ultimately collapse into a Milky Way type of system. Okay, so you put all your particles, all your computer simulation, all your power into this small region on high resolution. The larger region is there just to give you some idea of the total gravitational tidal field. Okay, these are simulations are called zooming. Basically, you have particles of different masses because your entire resolution simulation box has got different type of resolutions. Okay, so if you simulate the halo of a Milky Way in cold dark matter, according to those prescriptions, you get something like this. I'm going to do this. Okay, so that's a halo of the Milky Way. It's a simulated halo, of course. We simulated that a few years ago. It's about 1 billion particles. Now it's sort of still state of the art. And you see the granularity of the dark matter halo of the Milky Way, which is a few hundred kiloparsec extent. And what you find in this type of simulation is that about 10% of the mass of the host is still in subclumps. Okay? So why is that? It's because smaller clumps collapse at early time in cold dark matter when the universe is denser. So they're extremely dense, they have Caspi profile, and so they tend to survive the tidal forces which will tend to destroy them. And so when you make a dark matter halo, and you look at what's the result of the entire assembly history today, you realize that the merging process is never complete. Okay, those clumps will survive. Okay, and so in the galactic halo, you have the entire recorded history of the assembly of that self-gravitating dark matter clumps in subunits. So about 10% of the Earth mass is still in subunits if we are talking about Milky Way type of halo, and the mass function of those subclumps has got a slope of -2, the differential mass function, which basically means you have equal amount of mass per decade of mass in substrate. So, okay, that's all nice. This is CGM. What's the problem? The problem is when you compare this type of simulations, then, I can count how many satellites, big clumps will survive. And let me make a cut at about 10 kilometers per second in circular velocity. So I'm using circular velocity as a proxy of the gravitational potential. So these are all, if you want, subhalos, dwarf type of subhalos, which are more massive than few by 10 to the 8, 10 to the 9 solar masses. Okay? How many would you predict in this type of simulation? About 1,000 above this cutoff. So if you look now at the halo of the Milky Way, you see about 25 satellites. If I look at the luminous component, the stuff that I can see in stars, perhaps in H1 or so, there are only 25 satellites in the halo of the Milky Way. That must mean that some of these clumps, which are in principle big enough to form stars, in fact, are not forming any stars. Okay? And that has given origin to the so-called missing satellite problem, where, of course, the term here seems to imply there are many more satellites that we've not discovered yet. Okay? Because the dark matter halo, in fact, is much more clumpy or lumpy than the distribution of luminous matter in the universe. So what are the solutions to the missing satellite problem? Well, you can blame gastrophysics. Okay? You say, fine, those dark matter halo are there because it's a prediction of cold dark matter, and I know that cold dark matter works well on large scale. So that's a unique prediction of CDM. The halos must be lumpy. However, I'm not seeing stars in those relatively big dwarfs, and that's because dwarfs are not very efficient at forming stars. And the reason for that, well, there is a variety of reasons. You can think a dwarf has got a shallow potential well, so if I'm forming a one generation of stars in that potential well, those stars will explode as supernovae, inject energy, that energy will sweep away the gas, and you quench star formation that way, for example. Another possibility is that there is an external UV background, and that UV background is basically photoionizing the gas to a temperature of 10 to the 4 Kelvin or so. And so if your dwarf has got a virial temperature, a gravitational potential, which is below the temperature of the gas, of course, that gas will not see that gravitational potential and will not fall into that gravitational potential, so it will not cool down and form stars. Okay? There are many of those possibilities. These are just a few. There are others that you might consider. In fact, on large scale, the idea is that we are quenching star formation in ellipticals because of AGN filter. Okay, we inject energy into the interstellar gas, and that will basically quench star formation. If you don't have any energy injection, if you don't have any feedback in your simulation, what you end up with is a lot of stars, too many stars compared to the data. Okay, gas will tend to cool. Okay, the amount of cold gas that there is in the universe today, it's tiny. It's only 1% of the total. And you have to have a way to keep that gas hot instead of cold. If you let it cool down, you get numbers that in fact don't fit the data. So that's one possibility. Of course, if you want to address that possibility properly, now I have to do, again, nonlinear dynamics, simulate galaxy, but with gas. Okay, now I have to solve the hydrodynamic equation. Things are becoming more complicated. I not only have a dark matter component, but I also have gas. Okay? So I need a technique to solve the coupled 3D gravitational dynamics of the cold dark matter as well as the radiative hydro of the baryonic fluid. Okay, there are several of those techniques available. You don't have to make a new one. There is smooth particle hydrodynamics over SPH. You can do a Greek code, something in between, which is a moving mesh. The problems of galaxy formation are not associated with the type of hydrosolver. They all work, they all have their bugs, etc. But it's not the hydrosolver that will solve galaxy formation for you. The problem is you need some subgrid phenomenological model for star formation. The gas is cooling down. You have to have a recipe that will tell you what is the fraction of that gas that is forming stars. And of course, when those stars explode as supernovae, you have to have a way to inject that energy into the interstellar medium. And you have to do that at a finite resolution. Okay, again, on the Milky Way scale, if you do a simulation with gas and cold dark matter, and that simulation is cosmological, the best simulation that we have so far had a resolution of 100 parsec, 80 parsec. Okay, that's state of the art. That's the size of molecular clouds. I cannot resolve anything on smaller scale. Okay, so you need to have some recipes that will tell you, in fact, when energy injection by supernovae is going into, for example, momentum of the gas producing galactic winds, as opposed to thermal energy, which is then immediately radiated away. Okay, so those are the problems of a recipe of galaxy formation from a theorist point of view. These are, I'm showing you some results of simulations of dwarfs. Okay, so we simulated a field of dwarfs. There were 7 dwarfs in that simulation, which made you know what I mean. And what happens is that when you inject energy into a dwarf, exactly as I told you, because the gravitational potential well is shallow, I inject supernova. Those supernovae are going to eject the gas to large distances, and this is exactly what you've seen here. It was a relatively big box. You can see a small dwarf there. This is the metal field. So metals are being vented by those dwarfs. Okay? These are, I think it's one of the highest resolution simulation of the dwarf galaxies, again, starting from cosmological initial conditions. So you didn't see initially the universe that was expanding, etc., etc. But you start at high redshift z equal 100 or so, you let it evolve down to z equal 0, and you hope that what you get with is something that resembles a dwarf galaxy. So if I make a plot of star formation efficiency as a function of halo mass, so this is stars, this is m star, the stellar mass divided by the mass of my halo, etc. In those type of simulation, you see that at relatively high masses, it sort of follows some curve which you would expect from just pure phenomenology. And when I went down to small masses, then I see larger efficiencies. We see larger differences in the efficiency of star formation at small masses, below 10 to the 10 solar masses or so. So the star formation efficiency appears to be modulated by the gravitational potential well. For these type of systems, the mass in dark matter, the difference is just a factor of 2 or so, but there is more than a factor of 10 in the stellar mass. Okay, the reason is it's a network of complicated feedbacks, which include supernovae explosions as well as ultraviolet background. There are systems below 10 to the 9 solar masses here that are unable to form stars. Okay, because the gas is never getting so dense, in fact, that you trigger star formation. Okay, so then you can say, fine, this is gastrophysics. This is an example of physics, of gastrophysics, where, of course, I'm not producing too many stars in systems that are too small, and that will solve my missing satellite problem.
Yeah?
Yes?
How many of those 1,000 expected clumps in the simulation would have a mass greater than 10 to the 9?
Oh no, a small fraction. So at 1,000, you get 1,000 of those systems at 10 to the 8, for example. Okay, so then you have to say, okay, fine, but if below 10 to the 9, all my systems, 3 systems at high resolution, below 10 to the 9, in fact, don't seem to be able to form stars at all. Okay, perhaps it's resolution, perhaps I don't have all the right physics. But then you could argue that in fact everything below 10 to the 9 would be dark in a proper simulation. And of course, I only have a few examples here because it's harder to do bigger simulation at this type of resolution, which was 80 parsecs.
A few should form stars also below 10 to the 9, right?
If you, in this particular simulation, there is nothing that does. Okay, in the real world, I don't know. You tell me. Why? Why? Well, first of all, we don't know that. This is viral mass, right? So we don't have a good way to measure that. And of course, no, the reason I'm saying that, of course, in the end of the Milky Way, satellites get stripped, right? So we don't know. So we know the mass perhaps have been formed, but not after it was accreted. Maybe you're right. I'm not saying that it doesn't happen. I'm just saying we just don't know. I don't know. Okay, there's another possibility. So, fine, the missing satellite problem could be solved just by the physics of star formation. Another possibility is you can blame cold dark matter. And one way to do it is to say, okay, I'm changing the properties of my dark matter particle. Instead of making cold, which means heavy. So this is our dark matter particle, they are heavy. If you want, they are cold, which means they are moving with small velocities. And so all the small-scale structure is preserved. If I don't want small-scale structure, I can make my dark matter particle warm. Meaning, because it's creating thermally, I decrease the mass of my dark matter particle. Here in this particular simulation, it is only 2 keV. Okay, 2 kiloelectron volts. Okay, so a relatively light particle. And so what happens is, because those particles, if they are created thermally, they will be moving fast in the early universe, they will stream out of small-scale perturbation. So now, if I do a simulation in warm dark matter, this is just n-body simulation. That's a halo of a Milky Way type of system in cold dark matter. That's the same halo in warm dark matter. What happens is, I don't have a lot of power on small scales in warm dark matter, and so I suppress a lot of those satellites, a lot of those clumps. They just don't exist. Okay? So then you say, okay, warm dark matter is perhaps a solution to the missing satellite problem. We know, of course, that the other extreme is hot dark matter, right? Something that is extremely light, is going to be moving even faster. Well, we know that that doesn't work. That has been excluded. You are not able to form galaxies if your dark matter particle is only 30 electron volts. Okay, fine, so let's say it's warm dark matter. Well, we have some information from the Lyman alpha forest, in fact, that warm dark matter doesn't seem to be working particularly well. So what happens here? What happens here is that, of course, we take the spectrum of a quasar at a high redshift, and we look at the absorption lines, which are imprinted as UV photons get redshifted and are absorbed by intervening gas. On large scale, that gas is mapping the dark matter distribution, so I can study the power spectrum in velocity space. This is a spectrum after all. In velocity space of those absorption lines, and see whether I can say anything about the properties of the dark matter particle. So these are simulations, for example, run by one of our colleagues, your colleagues, Matteo Gil in Trieste. And so these are simulations where you do mock spectra. This is flux as a function of velocity. And what is done is do simulations of the Lyman alpha forest in 3 particular cases. Lambda CDM, so this is called dark matter in green. then a warm dark matter particle with 2 keV, and a warm dark matter particle with 1 keV. And what you see here is that high frequency power, small scale fluctuations, are present in cold dark matter, but they're not there in warm dark matter. For the same reason that, again, those fast-moving particles will erase small-scale fluctuations. And you see that in the spectra of distant quasars. So now let's take a power spectrum of those lines, and this has been done, of course, by Deal, using his simulations, and compare that with data which comes from high-resolution Keck and Magellan spectra up to redshift 5.4. So redshift is going up in this direction. You might not be able to see. This is redshift 2, this is redshift 4, this is redshift 5, and these are power spectra, the data, as you can see. And the simulations in green are cold dark matter, and the simulation in red are warm dark matter. And you see at high redshift, and of course scales is becoming smaller as I go from left to right. And at high redshift, in particular, what you can see is that lambda CDM does very well when you're reproducing those small-scale fluctuations. But if I have a warm dark matter particle of 2 keV or so, then I run out of power. This is not a good fit to the data. And in fact, you can do a statistical analysis, and then you basically can say that the 2 sigma lower limit on the mass of a thermal Rayleigh in warm dark matter must be greater than 3 keV. Okay? If it's less than 3 keV, you can't explain the small-scale structure of the Lyman alpha forms. 3 keV corresponding to a cutoff mass, if you want to prefer to deal with halo mass, of about 3 × 10⁸ solar masses. Okay? So I can suppress structures on scales that are smaller than this and still fit the data, but not larger than this, otherwise I don't get enough small-scale fluctuations in the Lyman alpha forms. Now it turns out that this lower limit is too large from warm dark matter to have much effect on the missing satellite problem. Those 1,000 halos that we were talking about were typically above a few by 10⁸ or so, okay, which corresponds basically to that. So I cannot use a particle mass of 2 keV because that's ruled out. If I go above 3 or 4 keV, then it's basically almost cold dark matter again. So warm dark matter does not seem to be able to solve the problem. There is another possibility, and which is of course favored by theorists, and that we blame observation. And I'm a theorist, but I have a point. And the point is that those 25 dwarfs that we see in the area of the Milky Way, half of them have been discovered by this low digital sky survey, which only covers 20% of the sky, and also is not particularly deep. So the expectation is the number of dwarfs, if I had an all-sky survey and was a deeper survey, the number of dwarfs would become higher. In fact, there is a recent results from the dark energy survey, 9, or in fact I think it's more than a dozen now, dwarfs have been discovered, in this particular case, close to the Magellanic Clouds. So it's possible that our tally of dwarf galaxies in the Milky Way, of course it's incomplete, and might go up from 25, I don't know, 50, 100, we'll see. We'll see what happens. Most astronomers, I would say, they would say that the missing satellite problem is a combination of 1 and 3. There are more dwarfs than we know of, and star formation in dwarfs is not efficient because of cooling and supernovae and feedback, etc. If that is the case, then you are left with the question, are dark matter halos really so lumpy as predicted by CDM? So, what's the answer? Well, when we try to understand stuff that relates to mass, gravitational lensing is a good probe, because gravitational lensing doesn't care about whether you're dealing with baryons or dark matter. It only cares about the potential. So, a number of years ago, in fact, I think Ben Metcalfe is here, so a number of years ago, Ben was in Cambridge, and we were talking about this type problems. And we realized, in fact, that there are a lot of distant quasars. So these are quasars. There is a quasar at high redshift, which is lensed by an intervening galaxy. It's a strong gravitational lens, so that lensing process will produce multiple images. Okay? So then you can model the intervening galaxy, the gravitational potential, with a smooth potential, like an NFW profile, you can have a triaxial potential, etc., etc. And if you do that, what you can explain are the relative position in the sky of the multiple images. But there are a few cases, in fact, typically radio quasars, where you can explain the positions of those multiple images with a smooth potential, but not the relative magnifications, the fluxes that you see at Earth. They are messed up. Okay, and so the idea would be to use those flux ratio anomalies because the magnification is proportional to the second derivative of the potential, while the position of those images is only proportional to the first derivative. So that means magnification is more sensitive to the clumpiness of your potential as opposed to the position. So let me give you an example. This is a quad lens. There is a distant quasar. There is an intervening galaxy in between, which is creating 4 images. Those are the observations. A, B, C, D are 4 images. Okay? And as you can see, A and B don't have the same fluxes. Now, when I do a lens decomposition of that particular, or reproduction of that particular case, what you have is this type of image, where the position of those multiple images, in fact, agree with the data very well, but A and B have exactly the same magnitude, the same type of flux. Okay? The observations, though, in the observation B is demagnified compared to A. There is no way these are radio lens quasar. There is no way I can change my smooth potential in order to reproduce this. Those are flux ratio anomalies. There are about 8 cases of this, not many. So, again, about 10 years ago, Dalala and Kochane made a study of those flux ratios and those multiple lens quasar, and they concluded that in order to explain those flux anomalies, you need to have a potential that is clumpy. Again, this is a simulation of an intervening elliptical galaxy which will be responsible for the lens. This is just dark matter granularity in the halo, but of course lensing is sensitive to projected mass on scales of 10 kiloparsec or so. So you worry about the granularity in a cylinder along that galaxy of radius about 10 kiloparsec. And that granularity must mean a substructure mass fraction of about 2% of the total. Okay, this is what you need to explain the data. And so then, of course, the question is there enough substructure in cold dark matter in body simulation to cause the observed flux anomalies? The answer to that is maybe. People don't agree. Some people run simulations and they say, yeah, it's sort of right. Other people say, no, there is not enough. It's a difficult problem. It's sensitive to, of course, the fact that lens may have some electricity. There is intergalactic small-scale structure, which is also causing some of those flux anomalies. You worry about the effect of baryons. There are not very many lens, as I told you there are about 7 of those. So to address this is just something that came out recently. This is a student, Daniele Fiacconi at the University of Zurich. He's been running now numerical simulations in cold dark matter of the halo of elliptical galaxies. Okay, and these simulations are typically about 1 billion particles or so. And what I'm plotting there is the outcome of those simulations. This is sub-halo surface mass fraction, which is a measurement of granularity as a function of distance from the center of those systems. This is the point that is required from the observation. That's Dalala and Kochane data, and this is what we get in the simulation. We get enough substructure in CDM to explain those flux ratio anomalies. This is just an body again. I don't have any free parameters. There, it didn't need to come out right. It could have been anywhere. In fact, if I were to plot the same quantity for a Milky Way type of system, I will get something that is below what is required by the data. Okay, Milky Way type of halo is smoother than elliptical galaxies because an elliptical galaxy is dynamically younger. Okay, formed later, there is less time for tidal forces to destroy those satellites. And so the typical lumpiness of an elliptical dark matter halo is much higher, at least much, a factor of a few, 3, 4 times, 5 times higher than you would expect on Milky Way scales. There are other techniques that people are exploring. That particular type of technique is statistical. It gives you some information about the granularity of the organizational potential. There are other techniques which rely on observing at high resolution the Einstein rings. So these are resolved galaxies, extended galaxies, and there is a foreground galaxy and an intervening galaxy, and they are aligned with the observer, and so you get what is called an Einstein ring. And you can look at the distribution of surface brightness of those rings, in fact, and you do a potential decomposition. And people are starting to see, this is also a project led by a competitor, this is Simona Vegetti and Max Planck, and you start to see by looking at these type of lens, this is HST data, this was an ALMA simulation, you start to see dark clumps popping out in the potential of the intervening lens. That particular dark clump has got a mass of about 10 to the 8 solar masses. Perhaps more exciting is to look at the future, the expected number of lengths in this particular table, quasars, in wide-field optical surveys. As I was telling you, we rely on very few systems. The number of lengths in the next generation of survey and telescopes, this is PAN-STAR, of course, Long Digital Sky Survey, JDAM, LSST. The number of lengths is going to go up by 2 orders of magnitude compared to what we have now. Okay, so the expectation is over the next decade or so, we can really start to use strong gravitational lensing as a probe of the granularity of the potential of the lens, and so if you want, as a probe of cold dark matter. Okay, those are just highlighting a few surveys and how the number of expected lenses is going to increase. There is another way, of course, to detect the dark matter substrate. If dark matter annihilates, then you have some hope to see the problem of that annihilation in the center of either galaxies or nearby dwarfs. Okay? And because the dark matter particle is heavy, when it annihilates, it's going to produce gamma rays. Okay? And so a few years ago, we made the prediction that the Fermi satellite would have seen, which is up there still, would have seen at GeV a lot of those clumps in the halo of the Milky Way. A few times of them would be close enough and big enough to produce enough gamma rays that would be detected. Now, of course, if that had happened, you would have known it. There is no detection of clumps in the Milky Way in dark matter annihilation. Not so far. There is a claimed detection in the galactic center. Okay? So what happens in the galactic center? Again, you have a large concentration of dark matter. You also see a lot of gamma rays, and this is our Fermi images. There are gamma rays that come from the interaction of cosmic rays with the disk. But those are anisotropic. You can subtract those out. And when you do that, you are left with a signal that is spherically symmetric around the galactic center. It's something that is difficult to explain with any type of astrophysical sources, and it requires, in the case of dark matter annihilation, a cross-section that is exactly close to the one predicted from a standard weakly interacting massive particle. Okay? So this paper has been out there for 1 year or so. Is this detection of annihilating dark matter. I don't know, but the physicists seem to be excited about it. Again, it's extended, it's well resolved by Fermi. It has a spectrum that is close to what you would predict by annihilating dark matter. There is a final problem that we run into when we do simulations, in fact, of galaxies in cold dark matter. Dark matter only simulation predict the density distribution, this is density as a function of distance, to be Caspi. It's called the so-called NFW profile, Y profile. It's an R to the -1, where the density keeps rising towards small distance from the center. Okay? Now, if we look at galaxy clusters, that's exactly what we see. Of course, galaxy clusters are, this is 1 megaparsec, 100 kiloparsec or so. You see that NFW does a relatively good job on explaining the mass distribution. Again, this is obtained by looking at weak lensing analysis, recent analysis by Ocadio. So, on cluster scale, the profile looks exactly what cold dark matter would predict. Now, if you go on dwarf scale, this is what you see. This is what you would have predict, a Caspi profile, you see a core. Okay, the density is becoming flatter in the inner region. Now, N-body simulation will never give you that. Okay, in cold dark matter, you get a Caspi profile. Doesn't matter how many times you run your simulation, you always get a Caspi. Okay, it's just intrinsic to the property of dark matter. We start to see now cores even in dwarf satellites. These are two examples. This is Sculptor and Fornax. They are the dwarf satellites of the Milky Way. Again, the way this analysis is performed is by looking at two different populations. There seems to be two populations which have very different chemical properties, very different metallicity, population of stars. Okay? And so you use those stars to trace the gravitational potential by solving the spherical Jeans equation. This has been done by Walker and Penarubia a few years ago. And what you can come out, basically, you can make a mass profile as a function of distance from the center of the dwarf. And you get those two populations, give you a profile like this. This is the expectation from cold dark matter. Again, you get a core instead of a cast. Okay, so what's happening here? Again, you can try to change the properties of the dark matter and try to create cores instead of casts. One way to do it is to assume that dark matter is self-interacting. So dark matter is weakly interacting with the baryons has got some self-interaction cross-section which is relatively high. And so in the inner region of galaxies, those dark matter particles are colliding often they are exchanging angular momentum as well as energy, and so you basically heat up the dark matter distribution and you create a core. Another possibility is to say, well, perhaps there are baryonic processes, in fact, that are causing this. So in the same simulation of the dwarfs that I was describing you before, if I make a plot of the star formation rate, that's in particular a specific star formation rate, as a function of time, what we get are an extremely bursty behavior. So again, this is simulation. What happens is gas gets towards the center, it cools down, it's forming stars, stars explode as supernovae, the energy injection from supernovae expel the gas, you have to wait for another accretion events, another star formation events, you get burst of star formation. Following this burst and this inflow and outflow, what happens is the gravitational potential of the mass in the inner region is changing. This is the mass within, about 1 kiloparsec or so, as a function of time, and the mass is changing following those inflow and outflow phenomena. On timescales that are relatively short. So these fluctuations are causing the dark matter to do something. Okay, let me show you what's happening here. Let's assume you start with a gravitational potential which is dominated by the dark matter, and it's an NFW, so it's a Caspi profile. You accrete the baryons, and of course you do that on long time scale, let's say. So it's an adiabatic process. And so following that accretion, your potential will become steeper. Then you get star formation, and that star formation is going to expel that gas. Okay, and your potential is going to become shallower. You end up with the same potential that you had before if the process is adiabatic. It's happening on time scales that are longer than the dynamical time scale. Okay? So you can see that effect by looking at a 1D exact numerical solution to a time-varying harmonic potential oscillations. And here all the changes are adiabatic, the potential is becoming shallower, you have a test dark matter particle that is moving in that potential, and so now the amplitude of those oscillations is increasing, but then the potential becomes steeper again, following another accretion events, and now the amplitude of those fluctuations is becoming smaller. At the end of the process, there is no heating. Okay, nothing has changed. Everything was adiabatic. I accrete material, I eject material. The profile of the dark matter has not changed at all. So this mechanism doesn't work. If I want to create a core out of a cusp, I don't know how to do it if everything is adiabatic. However, the ejection of material, as we know from those simulations, the ejection of gas following a star formation episode is happening on time scale that are much shorter than the dynamical time scale, and that's a non-adiabatic process. So let's look at what happens again when it's not adiabatic. So now accretion is still going to be happening on slow time scale, adiabatic time scale, but the ejection of material is going to be non-adiabatic. So that sudden blowout, the potential became shallower, larger amplitude, so energy injection in my dark matter particle, and then adiabatic recondensation following the accretion of gas. At the end of this process, I cause some heating in my dark matter distribution. So it's a subtle process that seems to be happening in those simulations. It's just the fact that two important time scales, the time scale over which I'm accreting my material and the time scale over which I'm ejecting following galactic means, are very different. So that has been put forward as a possible way to heat up the dark matter distribution by Ponce and Governato. That's exactly what we see in our simulation of the dwarfs. Again, so what I'm plotting here is the dark matter profile as a function of distance for 4 simulated dwarfs, and those dwarfs have different masses. This is stellar mass. Okay, when I simulate those dwarfs in dark matter only, I get a Caspi profile, and that's the gray curve here. But once I include baryons, star formation, feedback, and the ejection of that gas in multiple episodes, I start to create a core because I'm heating up the dark matter. So to inject enough energy via supernova in that dark matter distribution, I need to have more than 10 to the 7 solar masses in star. Okay, if I drop below 10 to the 6 solar masses here, I have the same Caspi profile with or without baryons, because there is not enough energy being injected into the gas that it's able to heat up.
The dark matter mass in those gases is about the same.
The dark matter gas, no, here, the dark matter, it's larger here versus here. These are not forming very many stars because it's a small potential. So these are typically 10 to the 10 solar mass system in dark matter, and here this is about 10 to the 9. And so they're forming less stars, so it's a shallower potential, but still you don't have enough stars to inject energy into the inner region and create a core. Okay? So, I'm basically done. That was basically to show, in fact, that baryonic processes can, in fact, change the distribution of dark matter. Okay? That's something that we learned over the last few years. So every time there is some disagreement between the data and your expectation based on dark matter only simulation, you don't have to say, well, cold dark matter doesn't work, we need another filter. You have to worry about baryonic processes, because on small scale, baryonic processes can have an effect, like the one I just described before. A sequence of inflow and outflow events. It's basically heating up the dark matter distribution in the inner region of dwarfs. And it only happens in dwarfs, so it's changing the dark matter distribution. And if you don't account for those effects, then you're always going to run out of problem. So astrophysicists basically know much. They understand some, but of course we need help to do better. So perhaps the young people might want to get into this field. So the evidence that the universe conforms to the expectation of the lambda CDF model is compelling on large scale, but it's still hardly definitive. We have a number of observational tests today which are spanning a wide range of scales. State-of-the-art simulations without and with variance are exploring the prediction of the standard model with increasing high prediction. It is the standard model because it does so well on large scale. Okay, don't be confused by, alternative mode or something like that. Okay, on scales of the cosmic microwave background, and on scales of clusters, and on scales of the large scale distribution of galaxies, CDM does extremely well. Okay, better than anything else. And there are no free parameters in CDM. You just have to assume that your particle is cold, the power spectrum then keeps going towards extremely low masses. There are no characteristic scales in galaxy formation. There are no free parameters again. So that's important. Which doesn't mean, of course, that it's right. It only means that we are right in calling it the standard model because it does well with very few parameters on large scale. In galaxy center, dark matter density are lower than expected. Okay, expected meaning simulations are producing galaxies that have central densities that are much higher than the observation. Okay, not only that, but small subhalos must be dark. They can't be able to produce stars, otherwise we would have overproduced the luminosity function of satellites in the Milky Way. There is a lot of granularity in the potential of the dark matter, and all of those halos self-gravitating, they are there at 10 to the 7, 10 to the 8, 10 to the 9 solar masses. We don't have very many dwarfs in the air of the Milky Way. The numbers disagree by a factor of 10, 100. It's difficult to reconcile that by assuming, in fact, that we are missing a few satellites because of our survey. And so the tensions between cold dark matter prediction and observations on small scales may be telling us something about the fundamental properties of the dark matter, which would be exciting, or perhaps something about the complexities of galaxy formation, which seems to me more likely at this stage. There is emerging evidence that a poor understanding of the baryonic processes which are involved in galaxy formation may be at the origin of these small-scale controversies. Okay, these small-scale controversies have been there for 20 years. This is not a problem that I have been creating or have been discussing over the last 6 months. The core-cast problem has been around for 15 years. The missing satellite problem exploded about 16 years ago when the first dark matter-only simulation showed that galaxy halo had a lot of substructure. Okay, so these are long-standing problems in galaxy formation. It is after 15 years or so that we are starting to think, in fact, that some of those small-scale controversies don't necessarily require us to abandon the lambda CDM method, but just to address the physics of baryon, which, if you want, is the physics of galaxy formation, with a much higher fidelity and with the right physical process. My personal point is that there is no showstopper at this stage for lambda CDM. Okay, there are more exotic possibilities like warm dark matter, where you decide that your dark matter particle has got a mass of few keV or so. You could have a self-interacting cross-section to create a core out of a cast. This might still be viable, but require careful tuning and do not provide any silver bullet. I have to fix the mass of my dark matter particle or the interaction cross-section out of the blue. Okay, just to explain that particular observation. And there is no fix that can explain all the observations. In other words, suppose I wanted to assume that the dark matter has got some self-interacting cross-section and create a core. I would solve the core cast problem, but I would not solve the missing satellite problem. I would still need to invoke some baryonic process, like ejection of gas, to make those dark halos, dark matter halos, warm dark matter halos, dark, without any stars. So there are no silver bullet. You're just adding some pre-parameters, which is not the right way to do it. There are great hopes that underground detection experiments, gamma ray observation, Collider experiment will identify the dark matter particle within the next decade. We have been saying that for a while. I like to retire knowing what the dark matter particle is, and I'm becoming more and more skeptical that that will happen. Is this the dark matter decade? Yes, we keep saying that. Of course, astronomers will continue their decade-long practice of studying the dark sector by observing and modeling the visible. My hope is that over the next decade or so, strong gravitational lensing will provide important evidence for CPM substructure. Again, over the next decade, many large wide area survey will increase the sample of strong gravitational lens system by orders of magnitude. And I showed you how gravitational lensing is providing information about the granularity of the intervening potential. And I'll stop here. Thank you.
One is about the core.
Yes.
I remember, maybe I'm wrong, that Oleg Ney also
Yes.
did some experiment with no positive results.
Yeah, it was not Oleg, it was somebody else. But yes, Peñarubia. Okay, so the question is, can you inject enough energy with supernovae to create a core? Some experiments have been run, and these were non-cosmological simulations. So you would start with a halo today as equals 0, which is massive. You assume it is initially cuspy, and then you inject the energy and you try to create a core. And what you have is that you run out of supernova energy. There is not enough. So what's the bug in there? The bug is, in a cosmological simulation, you never have a cusp. At very early time, dwarf galaxies form a lot of stars at any time. They have all stellar population. So a lot of injection of energy is happening at redshift greater than 3 or so, when the gravitational potential is still shallow. So you start to create a core at early time, and then once you have a core, it's always easier to enlarge that core. Okay. So it's a time-dependent process, and it's incorrect to assume you have 10 to the 10 solar mass dwarfs, which is cuspy, and then you have to create a core. That 10 to the 10 solar mass dwarfs never had a cusp in the first place, because it formed a core at redshift greater than 3 when it was 10 to the 9, and then it becomes easier to enlarge an initially flat distribution, because the escape velocity is smaller.
And as a very short, just a curiosity, how do globular clusters fit in the
They don't. Globular clusters never fit in anything.
So they are not a solution at small scale?
So they are not, no. I might have a model. Well, I'll be happy to run it with you. Okay, so globular cluster. You have star formation with high efficiency, and there is no evidence for dark matter. Okay, so how do you create 10 to the 5, 10 to the 6 solar masses in a system that doesn't have a dark matter?
With a velocity dispersion of the order of...
With a velocity dispersion, that's right.
But you have ultra-faint galaxies.
Sorry?
Ultra-faint galaxies, they are massive, quite massive, they have stars.
Ultra-faint galaxy, yes.
They are peculiar in metallicity, they may have dark matter, so maybe they are...
Yeah, but the velocity, that's right. So the velocity dispersion there is so high that there is dark matter because
So
the stars
this
are
may be a
not.
solution
In
or
the
not?
case of globular clusters, you don't have that.
Let's leave out.
Okay, let's leave globular clusters. Let's forget about that. That's for stellar astronomy.
Yeah, okay. This is my point. Our ultra-faint are more interesting in a sense.
Yes, but ultra-faint, again, there is a dozen ultra-faint galaxies. Okay, I would predict from an N-body simulation
And around
1,000 ultra-faint.
Yeah, around galaxies you have many streams, you have strange
That's right.
things
So,
which may be
yes.
important,
Yeah, so those
Maybe
are...
that you can
those
pick up
are-
a galaxy, but you can pick up streams.
Yes, but that requires a lot of dwarfs to be destroyed. And of
Why not?
course, Well, that would happen in the simulation. I don't have to put it by hand, right? I mean, I have a fraction of the dwarfs that is
So
destroyed.
maybe that most of the matter is in streams, so that they are around the galaxy.
But that's not what the simulations are telling me. Why don't they get destroyed?
Simulations are wrong, who knows?
Yeah, but how? This is I'm telling you, there is no free parameter. It's an n-body. They get accreted. I get a halo of the size of the Milky Way. I must, you know, that's gravity. Tidal forces is surely what I can resolve. So I am destroying them, but not in enough number, because at the end of the day, by z equals 0, I still have 1,000 of them left with circular velocity of 10 km per second. Yes, a lot of them have been destroyed, but I'm talking only the ones that are surviving. So destroying, you know, tidal destruction is happening, but I don't see how to make it more effective than in the simulation. In fact, if I had baryons, I would expect tidal disruption to be even, you know, less efficient.
Filippo.
Yes, you haven't said anything about the so-called too big to fail problem.
Yes.
Do you think it's not serious?
I didn't say it because I was running out of time. So that's your answer. I knew somebody would ask. So that's why okay, so the too big to fail, it's again, it's a kinematic problem where you look at your n-body simulation, you look at the velocity profile, circular velocity profile of your dwarfs, and you compare that with the velocity profile of the dwarf satellite of our own Milky Way. Okay, and that comparison is shown here. These are the, so this is the inner, this is not the circular velocity far out in the air, this is just distance from the center in kiloparsec, and that's basically where some of the dwarfs lie. Those are the points there. Okay? N-body simulation will tend to produce systems that have much higher velocities than is actually observed. Okay? The more massive systems have a lot of dark matter in the center, and so the inner circular velocities are too fast compared to observation. Now, why too big to fail? Because these are the most massive systems, but you can't solve this problem by assuming they're going to be dark, because it doesn't make sense. The small systems are going to be dark. The more massive systems should be luminous. They are too big to fail in forming stars, and so they should be there, but we don't see them. Now, the same process that I was telling you is creating cores. It's also, when I run the same simulation with baryons, those cores imply circular velocities that are much lower than what I would expect in n-body simulation. So just to give you a quantitative answer, these are the same simulation n-body, okay, the red one and the green one, no gas, and this is the same two systems once I have hydrodynamics and feedback. And you see the circular velocity profile has dropped by quite a bit. Because it's a core.
It's the same solution.
It's the same solution. So the same solution that is creating the core, it's also, of course, decreasing the central velocity, because that's what a core is, the circular velocity is low. And because it's in the massive system, then you would expect a lot of stars, a lot of supernova injection. So then the cores are big enough to explain the too big to fail. So I was never a fan of the too big to fail, simply because those are the systems where we know there are lots of stars and we know that baryonic processes can make a difference. Now, of course, if I were to be able to see cores in extremely faint dwarfs, which don't have very many stars, mass to light ratio 100 or so, like Segway 1 or Willman 1, if you see a core there, then that's impossible to explain with baryonic processes. It's star formation and feedback, simply because there are not very many stars in the system. So below the 6 solar mass in stars, I give up. If somebody comes and show me there's a core there, I'm going to say, you know, it's not baryonic. It's something else.
I just wonder, what do you think about the fact that if you look at the stellar population of the halo and the dwarf galaxies, those that are the most candidate to be building blocks, they are different.
Yes.
And you do this kind of analysis just taking the very old stars, so those that should resemble each other. So how do you explain it?
How do you explain the difference in the stellar population properties between the halo and the dwarfs?
Yeah, if you can. I mean, it's not only the missing satellites, it's also also that the one that we see around our galaxies have different properties of our galactic halo.
Yeah, that has been around for a while. I'm trying to remember whether we said anything smart about this. I don't think so. What I can tell you is that when I simulate dwarfs in the field, not as satellites, okay, and then I look at the H1 properties, mass metallicity relationship, properties of metals in the interstellar medium, we do a decent job at reproducing the data in the field. Okay? So that probably means that some of the recipes that we are using are sort of making sense. But whether now when those are accreted into a bigger halo, whether I can explain the chemical evolution of the Milky Way at that level of precision, I can't. I don't have the data, the simulated data.
Yeah, I see. Anyway, what we can learn from stars is that, for example, maybe it's more probable that the big satellites are better resembling our galactic halo than the classical dwarfs, let's say from Fornax to the less massive one. This is, from our point of view, we don't have any way to form the full halo using.
The other thing, of course, to remember is that being hierarchical, you are accreting those systems over long time scales. They're not just accreting in one accretion episode, right? So they will evolve chemically.
This is true, but I'm not talking about only chemicals, but also just the properties of the blue horizontal branch stars that are the oldest, so they do not evolve. As we see them in the quark, we see them in halo, and they look different, really different.
Yeah, I wish I could resolve blue horizontal stars in the world. I'm not there yet. But I take your point. I take your point. And I think we're going to learn a lot about the stellar halo, from Gaia, for example. So these are exciting times to start worrying about those things. And in fact, I do have a student that is back not to satellites within the Milky Way halo, more the stellar halo overall, because resolving satellites to that type of precision, it's very hard.
Yes, I have just a curiosity about the strong-axing quasars to probe subtraction. We know that the multiple images, there is a tiny delay among them, and we know that quasars are typical by sources.
Yes.
So we are going to measure the ratio of fluxes, no, it doesn't matter, but we know that it also variability.
Yes. Yeah, that's right. So there are, you are right. You can look at time delays, and of course they are also telling you something about the granularity of the system. Time delays are sensitive to the potential, gravitational potential. Positions of the images are sensitive to the first derivative. Magnification of every image is sensitive to the second derivative. So if you want to address the clumpiness, you're always better in looking at probes that depends on higher derivative of the potentials, because those are the ones that are sensitive to the lumpiness. But I agree, there are a variety of lensing probes that you can use to look at substructure, and people have proposed that. So yeah, there is an active field. That's an active field. Some people are also, looking at star-forming dusty galaxies, which are lensed as a probe and can be observed by ALMA as a probe of substructure. So yes, I agree. It's not just flux anomalies. Besides, flux anomalies is telling you an integrated quantity, which is the total clumpiness. It doesn't tell you about the mass distribution. So, some of these techniques, in fact, are just telling you about, what's the mass of an individual lump, like in that HST, ring satellite. So those are the best techniques. They're just being developed as we speak. So it'll be exciting.
Flavio?
Just a last curiosity.
Yeah.
According to your scenario, which is the upper limit of the dark matter particles now?
Okay, so that's a good question. So how far? So from Lyman alpha forest, it must be heavier than 3 kV. Okay? So how much heavier? For the standard dark matter searches for WIMPs, we're talking about 100 GeV. But I don't think we have any probe of the distribution, of the dark matter distribution on scales that are less than 10 to the 7 solar mass systems. So to some extent, 10 keV for us, for astronomers, is already cold. Yeah. There's no difference between, if there was a sterile neutrino, which people have been talking about, which is 7 keV, already probing that versus 100 GeV with astronomy or astrophysics is just hard, because you have to go to very low masses. So in other words, what I'm trying to say here is that about 5 or 6 keV, we don't care, because for us it's just cold dark matter. It behaves like a cold system. Of course, from particle physics point of view, it makes a lot of difference. Yeah. But we don't have any probe about 5 keV. Currently, a 4 keV particle will still be okay with the data.
So, Carl, at the beginning of the talk, you were mentioning that the dark matter only simulation might be suitable for the dwarf galaxies.
Yes.
Because they are dark matter dominated. But in the rest of the talk, you were showing that on the dwarf scale, the baryons are very.
That's right. That's right.
In which sense you were saying that?
Well, again, on scales of a core, which is 1 kiloparsec, even in the dwarfs, you worry about baryonic processes like I was telling you that. However, a dwarf can be 5, 6, 7, 8 kiloparsec in size. And so on those larger scales, then N-body would do. It's just, what type of processes we're trying to address. So when I was saying it's okay for the dwarfs, I didn't mean in the inner region of the dwarfs. I meant overall for the dwarf distribution, how many there are.
Stripping, for example.
Stripping, tidal, how many survive, etc. On those large scale, N-body will do. If I want to look at the profile within half a kiloparsec, then it's all baryonic physics. Then N-body won't have.
Okay, well, Tony.
Yes.
Okay, when you work with advanced simulation, cosmological simulation, you use only dark matter particles, and then others.
No. The hydrodynamic simulations of the dwarfs, they were also cosmological.
Yes, but you don't have, for instance, the dissipation of gas or the formation of the disk, the stellar disk.
I do.
Yes. Okay.
Not in the N-body, in the hydro one.
Okay,
Yes.
in the I1.
Yeah.
For instance, when you form a compact disk, it will affect the disk shocking effect on ultrafine. So the destruction rate could be increased by this because of the stellar disk.
Yes, that's right. Now, yes. So that's a process you may wonder whether it's going to destroy satellites. But then you can look at the orbits of those satellites, and you can ask yourself, what is the probability that one satellite is going to interact with the disk? The galactic halo is 300 kiloparsec or so, 400, and the disk in size, the stellar disk, has got a exponential length of 2.5 kpc or so. So it's only when you have radial orbits that get very close to the center that that process can in fact affect distribution. There are not very many satellites that will get that close. When you talk about the overall distribution in the galaxy halo, it's a tiny fraction that will interact with the disk. The rest is just out there, like LEO T, 400 kpc. Those systems will never interact with the disk. So most of those satellites which are creating the missing satellite problem, in fact, are far away, like 50 kpc, 100 kpc. A tiny fraction is interacting with the disk. But yes, if they're interacting with the stellar disk, you worry about them being destroyed. It does not change these numbers.
So if there are no other questions, let's thank